Welcome to today's webinar. The topic today is how to integrate artificial intelligence to RFEM using API. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, new features on the website, and so on, newsletters. Yeah. I will be the moderator today and will answer your questions together with Dogukan, but my two colleagues can introduce themselves.
Yeah, hi everyone. My name is Dogukan Karataş and I'm leading the team for API and AI in München. And today I'm going to reply your questions in the chat.
Hi everyone, also from my side, my name is Michael Kraus and I'm also part of the team in Munich and I'm an AI specialist and I'm really looking forward to this session with you.
Okay, and Michael will do the presentation and we can switch off our webcams that the attendees can see the full screen. Before I hand over the screen to Michael, I would like to introduce you that panel that you can see on the right side of your screen. You can show it with that arrow here, and then you can enter a question here. Yeah, and we will answer you. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, I hand over the screen to Michael.
So let's see what screen you see. I don't know.
No, that's not the correct screen. The other one. Okay, that's quite okay.
You see the presentation now, right? Okay.
Yes.
Cool. So I'm really looking forward for this session because I think we have quite some new stuff to show, and we have some live demos here. We have some pre-recorded things, and first we will kick off this webinar with some words about the web services and the API, which is the foundation for all what will be then the main part of that presentation concerning artificial intelligence, machine and deep learning, and how we in Dlubal are going to use that, or you can already use that in some parts. For that we will get a bit of a background on AI, like what is that, so that everyone is on the same page when we dive into a bit more technical depth when it comes to using AI for optimization of your structures. And then we will highlight some of the upcoming features in the Dlubal universe, which is a help chatbot. We will have some experience with the text to model, and then I will quickly tell about future plans, what we are going to release during the next year. As already said, feel free to answer or post some questions. We're happy to answer that. And let's jump right into the API and web services. As far as I know, there have been some webinars already concerned with what web services are. I think Dogukan presented that very nicely to all of you. I will just take a chance here to summarize the main points. So what is an API? In short terms, API stands for Application Programming Interface. And this is a set of rules and protocols mainly for software programs in order to be able to communicate with each other. So it essentially acts as a messenger, facilitating the exchange of information between different programs or services. By receiving some requests and translating them and returning responses, it enables the smooth transfer of data and functionality between different systems. And if you want to consider that a bit more plastic, consider just a simple GUI or graphic user interface that also serves as a communication protocol, but this time between humans and software programs. So in simple terms, a GUI, and with a GUI, you can just interact with a program using buttons, menus, and other input methods. And in that same way, an API allows software programs to interact with each other and providing a standard set of rules and protocols for communication. So that was a bit more of an abstract intro. And now let's say you want to use that for RFEM. And with that RFEM interface, you can give the program commands using buttons and inputs. And with the API, you could similarly enable the communication between one software program and the other, like VS Code, which I'm using with Python to do that. And you will see that a lot in this webinar today. Yeah, so an API is basically a communication interface. And now what is web services? Yeah, simply web services are a type of application programming interface, API again, that distinguishes itself from other types of APIs based on their style and way of communication. Web services facilitate the XML-based information exchange between systems. Here in our case, in the Dlubal universe, we use an HTTP technology called Simple Object Access Protocol, or SOAP in abbreviation, to establish this connection, which provides a standardized method for accessing our web services. And in the past, and I think that was mainly with Dogokan and the team, they developed frameworks that enabled the use of these connections in structural analysis and design, because they provide basic functions that allow the users to send commands to RFEM and receive the responses from that. Yeah, having said that, feel free to browse into our GitHub repository. There you will find all that things what I just said, and you can play around and code along. And yeah, I really can just invite you to have a look at these facilities. They're great. And as I said before, this is really the basis of what is going to be shown in the AI part of that session. So still, I want to take the chance here to display the functionality. So in the best case, you should now see in the screen a programming code on the right-hand side and the RFEM GUI on the left-hand side. Dogokan or Andreas, can you quickly tell me if that's going to be seen or not?
Yes, this is the right screen.
Yes, okay, cool. So yeah, let's quickly dive a bit into that example. So as I said, the web services and the API, they can be used to communicate with RFEM, right? And this time we are not using our mouse, the graphical user interface only. No, this time we are using code to exchange information back and forth. And to quickly summarize a bit that script, the little thing which I brought to you, that is about cantilever beam under a point load. And I will walk you a bit through that piece of code. So as ever in programming, we first have to load some libraries here, mainly functionalities from RFEM. So we need some basic objects to establish nodes and so forth. And then we want to have some load cases. And finally, we want to collect some results. So this example here, the situation is that we have a list of sections here that is 3 IPE profiles, which we want to compute under a certain load. So we define this section list that can be shorter, that can be longer, depending a bit on your specific application case. And then we set the modification of the model to true and call that model just a steel column. And we initiate and instantiate a result ticket, which is empty in the beginning. And then we want to compute these 3 sections here in a for loop, as you can see. So the first thing to do is let's define some nodes. So we have a first node here, which is at the origin in X, Y, and Z is equal to 0. And then we have a 5 meter long column in that case. We want to assign a material. Here it's a simple steel S235. And this material here is assigned via this text and a material number. Then we're going to define a section. In that case here, as it is very simple, we only have one section. So we give it the number 1. And for the name of that section, we define it per this list and the actual counter in the for loop. So having the nodes and the material and the section, now we can define a member, as you can see here, all the attributes. And finally, in order to make it a feasible structural system, we need to give a nodal support. Here we just would clamp it at the first node. Then we can jump right into the load case definition. Here we define a load case 1. We exclude self-weight here, and then we put nodal force onto the second node and the direction of global C with 3 kilonewtons. Then we execute the computation and save the results from the RFEM computation, delete the model, and go into the next counter. Having done this for loop, we collect the results and just dump it into a JSON. Here you can also save it into pandas format or CSV as you like. But let's leave it for the moment and just give it a try. So I will start that script. So you see here it connects to the web service server. Hopefully it should now start to modify a model here. Yes, it works. Very good. And as I said, so it will take the first section from that list, create a model, apply the loads, do the computation, and save the results to this dict. And after the 3 computations have been made, we will hopefully see here this resulting JSON file. Yeah. And if you look a bit closer here, you can see that it actually is changing. So we are at the moment in the second run, and then hopefully we should see the IP 600. Yes, we do. And we are done with that computation. Yeah, and we are saving the displacement at the tip in meters. And you can see here, okay, finally, we really got out these results here, and we can now go further and do maybe some other analysis with that things. Yeah, I hope the workflow here got clear. As I said, if you have more interest in learning about the web services and how to use the API in maybe more complicated situations, feel free to check our other webinars, the recordings of that, or just put some questions into the chat box because Dugukan and Andreas, they're happy to answer those. Yeah, as you can imagine, we have now a big source of data, or we can generate a lot of data, which, yeah, the next step would be, can we use somehow AI in the widest sense for that? So at Dlubal, we had the idea of diving more into that realm and identify the useful cases of machine and deep learning for structural engineering. Because there is, yeah, I would say a big hype at the moment about AI, and a lot of times in the media you potentially see these what I call expectations here, like robots working with a computer on fancy stuff and graphics. But in reality, if the one or the other person in the audience already had to do with AI in the widest sense, they know that in reality it is a lot of working with code, and except you're a robot specialist, you will not really work with robots if you deal with AI. So the reality is that AI means a lot of coding and how to work with data. And that is why I wanted to stress a bit also the history of AI, because what we are seeing at the moment, it's not the first hype in AI. It's actually, I think, the third or the fourth AI wave, because AI in theory or in the sciences is a really old topic. So it began in the Second World War with some famous mathematicians in Great Britain. They already started to think about machines which can execute things on their own or reason about data. And over time, so there were some winters, AI winters, where some of the AI hypes broke down again. And it was really in the 80s, I think, were these terms, machine learning and deep learning, which is more applicable in the engineering sciences, where they came up. And yeah, so in AI in general, you deal with different kinds of software and programs. They can be symbolic, they can be data-driven. And this time we want to focus more on the data-driven side of AI. And this is more machine learning. And recently, since the last decade, especially, it's deep learning. Yeah, for your information, or maybe you know that, algorithms like neural networks, they have been like known even in the 90s or in the 80s. People did not simply have the computational power to train them or train bigger networks. So I think what we have seen in the last decade in all these AI breakthroughs, I would call them, that I think is mainly as we have computational power in our days at a certain amount of cost, which a lot of people can afford, and we have computers being fast enough to do all these computations and handle big amounts of data, and we can store them in a cheap way. So I think there is a good chance that nowadays we don't see this AI boom dying again, as it happened in the past, as I said, 2 or 3 times. And therefore, I think it absolutely makes sense as civil engineers or people in general to dive a bit into what that AI thing is. So I think it is important in a technical environment to reason if we should use AI or not, because in the technical sciences, we have a lot of models, and the question always is, or in the business, the question always is, why would you use another model if you have already some and they do a job? So if we want to use AI, you have to always check 3 things. So the first is, do you have data about the problem? Do these data contain the pattern you're trying to model? And is there not a simpler model which does the job? Yeah, if you can say yes to all of the 3, then you're lucky and you can apply AI, or at least there's a high chance of being successful in applying some kind of AI method. What you see here is, why would you in this AI boom still need domain experts like civil engineers? And I think the reason is because just people from the domain, like from civil engineering, yeah, they can judge these 3 things, like if the data is correct, if there is no simpler model, and if the data have or contain that pattern. So yeah, I think that in the future we will see more and more applications of AI within the domain, but they can never be developed without the input of the community. So that's another thing why I think we from the domain as civil engineers or architects should engage with these kind of methods. Yeah, I don't want to do too much of a lecture today. I just wanted to give you an overview of the nomenclature, because a lot of people talk about AI when this term does not mean really much. So if you want to be a bit more specific, and especially at Dlubal, we want to come up with software and programs which help you. Therefore, we wanted to establish a kind of nomenclature so that everyone speaks the same language. So let's start with machine learning, which is the older family of AI methods. And machine learning would be distinguished into two main categories of algorithms. And the distinguishing factor of the algorithms is the data you have. And depending now on the nature of the data, they would be then called supervised machine learning algorithms or unsupervised. So let's start with supervised machine learning, because I think a lot of you during their studies have already been in touch with regression problems. And that's really whoever did higher mathematics or something in that direction or statistics, you have basically seen some basic machine learning algorithms if you ever did polynomial fitting or so. And machine learning offers a wider range of algorithms, but at least you understood the basics concepts of that. So let's start with that regression example to clarify a bit what I meant with sorted or marked data. So sorted or marked data mean that, for example, I have some input, which is typically called X. And for each of the inputs, I also have an answer or a target Y, right? So my data set consists of inputs X, which I hand to that function or model. And then this model can predict me something. And I compare this prediction with an actual target or my label or mark in the data set. Okay, so I hope this clarifies that a bit. And the difference between regression and classification is just the nature, the data type of the targets of the Y variable. So if you have a Y variable which is continuous, that's regression. And if it is a discrete thing, then it's classification. As you can think of, hey, if I have maybe images, that would be my input, and I have a label, which is a dog or a pig or an ape here. The labels dog and pig and ape, that would be the marks or the labels. Okay, so I think we settled the supervised learning a bit. And if you don't have these labels, for example, you just have a lot of images, but you don't have a label for each of the images, you still can do machine learning here. That would be called the family of unsupervised algorithms, as we don't have access to a label. And typical things in data mining is just clustering, right? So give me a bunch of images or texts or models which have some similarities, but I would not know from the algorithm that these kind of data is dogs. It would just tell me, hey, here, this bunch of data that looks similar to the algorithm. So you have to feed that maybe then to a human to interpret the clusters. Another big thing is dimensionality reduction. I think most of you know compressing images. Yeah, that's the same idea. So whenever we can get rid of data representation features, we use dimensionality reduction to compress, so to say, the data to its main features, which is usually the direction of the data with the highest variance here. And then there is some association, machine learning algorithms, for example, in recommender systems and things. And yeah, I would leave it here with the machine learning. As I said, if you have in your education already got into contact with linear regression, you basically understood some of the concepts of machine learning. And now you can imagine that for the different situations what we have just looked at, for example, classification, regression, and clustering, there is a whole bunch of models which we can apply our data to. In order to not overcomplicate it, and as I said, I don't want to give a scientific lecture today, I just brought this example because we will look at it from the machine learning, but also the deep learning perspective. And what I want you now is to imagine that we have a problem at hand which has two input dimensions. I just called them x1 and x2. So that could be a length, that could be a profile, whatever. And I want you to understand that our target, our Y, that's a bit of a nonlinear problem. So some of our data lives here. Maybe that's columns which are buckling, and maybe that's columns which are not buckling, for example. And now we want to find a model which can describe, given our inputs, a prediction of our targets, of our why. Yeah, and I used the decision tree here classifier to distinguish if that thing will be in this class or in that class, given that nonlinear input space. And you see that there is this rough capturing of that circle. I still could play a bit around with that. But the point is that in AI, usually machine learning is a bit restricted in terms of expressivity, because there are the simpler form of algorithms and the more powerful form of algorithms are neural networks. And that's where the big breakthroughs, I think, came into place in the last decade, especially in computer vision, meaning working with images, videos, natural language, and so forth. So I want you to understand at least the basic parts of deep learning. So as I said, deep learning historically was a part of machine learning because we deal with a very specific kind of model, which is the neural networks, what you can see here. And meanwhile, it got so famous, or a lot of people worked in it, so that it is at the moment considered an independent field of science within AI. Yeah, what is a neural network? Again, we would have some input layers. That is where you feed your data into. That can be images, that can be text, that can be videos, that can be a lot of data formats, what you can think of. And then we have that layers in between here. They are called the hidden layers because, I mean, you can look into them via your code, but usually people would not know necessarily what has been learned inside it. And then what you can see as a human, again, that's the output layer, and that is where our output of the model of the network comes out. As I said, that can be an image, that can be a text, that can be your structural Dlubal model, and the output then could be any data type you want. Can be also an image, can be also a text, can be also a Dlubal model. And here you see again the differentiation between supervised and unsupervised learning. So when we have access to true labels or true marks, then we can do supervised learning because we can formulate this loss between the model prediction and the ground truth data what we have. And neural networks here, they are trained. So these layers are trained, meaning the numerical values between these nodes here, they change depending on how well our model can reproduce the training data what we gave. I hope you at least got some glimpse into what neural networks are. And as I said, that is really a big field at the moment. There is different models which everyone uses. So the students in the university would maybe look more into these simple things. There is things which can carry some time dependency. There is generative things. For example, everyone knows ChatGPT or so. Yeah, they are based on some of the more complicated neural network models, or if you work with images, you have maybe come across convolutional networks and so forth. Yeah, so for the ones interested, look at this. I think that's a very nice introductory page on neural networks. It's called Neural Network Zoo because it's like in the zoo, you go around and you, so to say, discover different animals, different neural networks. And as a start, I think that's very nice. Okay, I think very last things into theory, again, about the training. So I think it's important that you understand for training AI, we need some data, right? So we have some inputs and maybe some outputs, and now we want to find a relation between those two, and we want this relation to be modeled mathematically or in the software with a neural network. So that's just, I would say, more complicated formula. And typically what you will see here is these so-called loss curves. That means how well your prediction of the model compares to the ground truth data. And typically you will see this drop in the loss. So that means the model is getting better and better and better at predicting several data instances in your data set. So it does a good predictive job, so to say. Yeah. Usually, if you put more layers into the network, it is being more powerful, meaning it can be trained better. And let's dive again into our example. So you remembered with the machine learning approach, we tried to find the decision boundary or model these two data sets here. And what I wanted to show here is if you take a very, very, very simple neural network, I think that's even worse than the machine learning model. So we would dismiss that totally as well. But if we go a bit up in complexity, we will see that now this model is able to capture the circular structure of that problem and even captures nicely these two surfaces here. And we see that immediately in the loss, right? So if you look here, so that would be the solid lines would be the first model. So even after some training steps, like 500 epochs of training, that would have a significant error still, and you can see it visually here. And the second network that has a really increase in this drop of the loss. And we could say that this already learned something very acceptable. Yeah, I did not play around a lot with that pedagogic example here because I want to leave it with the theory. And yeah, if you feel that you have questions on that, feel free to write to us. We're going to maybe also consider to write a textbook on that and how we apply these things in Dlubal, but that will be stuff for next year. Yeah, closing remark on the deep learning side, as I said, the main difference in deep learning and machine learning is that in machine learning, you as the human expert, the human modeler, you're coming up with the description of the problem, meaning you're defining what is X1, X2, and so forth. And in deep learning, you can leave that totally to the neural network. And especially for images or videos or text, creating, so to say, a coordinate system of how to describe that properly, I think it's very hard. You as a human have a very hard time to do. And I think that's really where deep learning shines. So extracting features like descriptions of that image so that in the end you can reach that prediction if, for example, the input is a car or not. Deep learning comes with a downside. As we get rid of that feature extraction step, you need more data. Right? In comparison to machine learning, where you can have as little as 100 or so data points to train a sensible machine learning algorithm, in deep learning, it's way more complicated. So usually, if you don't have other regularizers like differential equations, you need simply more data because these feature extraction steps that will happen in the first layers of the network. And you can look into that, for example, in the ImageNet. There is some visualizations what these kind of networks have learned. For example, in the first layers, you will recognize that it has learned that the car is composed of tires or circles and so. Good, so far for the theory. And now let's connect back to our domain, to the structural engineering. As I said, since beginning of that year, we had that hype in especially, I think, ChatGPT and DALL-E, which both come from OpenAI. And these kind of models, like the transformer models, which ChatGPT or the GPT stands for, they have been around even before OpenAI, but I think OpenAI managed something very nice. They brought a new interface to these GPT models, right? Because now they provided us a web interface, and that's a bit similar to our web services idea, bringing in a new interface, and then people can interact in new forms with existing software. So I did the following. I said, like, hey, if we have these powerful transformer models behind that company, can we use that to do something meaningful in our domain, like in civil engineering? And I just asked DALL-E to construct me a sustainable concrete bridge over a river. And you can look what it came up with. So that is just two examples out of some. And if we look to the right, I mean, I'm from here, the Munich area, or at least Germany. So for me as a civil engineer, that I think is more of a US style in designing a bridge. So I think in Europe, you will not see these kind of head here and stuff. But more severely, as a civil engineer, you would ask yourself, why the hell is there a column in the middle of that span? On the other hand, if you look a bit to the right-hand side, which I think is a more spectacular bridge, I can barely find concrete, or at least I imagine this to be steel, or I hope that is steel. But these hangers here, they just end in nowhere, and also that thing here goes into the bushes. So my take is, okay, it's a nice start, so meaningful to some extent, but we as engineers should now start to contribute to that stuff. And you may remember my circle with the scientific machine learning. I think that's especially what we should do. So for the strategy in Dlubal, we could ask ourselves, like, why would we as civil engineers use machine and deep learning at all? And we said, okay, I think it makes sense to use machine and deep learning if we have just empirical models anyway, so there is no like differential equation like the background of the finite element method, or if you want to describe newer materials where we know that physics-based models maybe are incomplete or not fitting the experimental data very well. Our design problem, that can be a length, that can be a section profile, that can be a material. And what we usually not know is this greenish surface. And the idea is that all of your structural models, for example, a bridge or a house or a truss, they live all on this parametric manifold. So if I change the cross sections of that cantilever, what we looked at, I would go along these lines here, right, on that surface. And what with FEM we do at the moment, we shoot at this surface, so to say, at single points. So whenever you do a structural analysis, you fix an input space and then evaluate maybe 1 or 2 points on that surface. But maybe you want to learn the whole surface, and then that would be called surrogate modeling, and then we can speed up optimization and analysis. Yeah, and that's the reason why Dlubal went into their offices and came up with a first optimization tool that is based on the particle swarm optimizer. And I brought you that little figure here on the right-hand side. So particle swarm optimizers are specifically suitable for solving extremely difficult or impossibly numeric optimization problems, can have multiple maxima or minima and things. And the update of the particles in their state variables, which is the position and the velocity, they are mimicking, or these update equations come from social behavior modeling, right? So they were inherited from there. And Dlubal went into their offices and programmed this particle swarm optimizer for structural applications. So there is a whole set of webinars, so I will spare a bit the time here to go further into detail. I just wanted to tell you, hey, in the background of that, we have worked on particle swarm optimizers and how we can use them within the Dlubal software families to allow for optimization under multiple minima and maxima. And I think Dogo-kan will provide you the link to the other webinars. Feel free to have a look if you want to optimize your structures with that technique. Yeah, there is an upcoming tool development, as I said. So far, the particle swarm optimizer does the following for you. So it samples a lot of these inputs and tries to find a local minimum here at the surface with that particle swarm optimizer. What we're going to provide to you is what's called an inverse design, meaning that you can request performances. For example, you want to limit your deflections to 100 millimeters and maybe a first eigenfrequency to some domain and maybe restrict some of the materials. And then this generative model will provide you the respective design features, what you would have have used to come up with these criteria here. So that's not possible at the moment with any standard solver like finite element method. So we went into our lab and did that to come up with a solution, and I brought you a little video here. And what we do here is we use again the web services. So we define again here a concrete column which has a length of 5 meters and some loading like dead load and live load. And we request here some utilizations in the limit states of serviceability, but also ultimate limit state. And then we have this generative neural network, which you will see in a minute. So you hand over these requests to that, as you can see here, and then it will generate, and you saw that it's really quick, a set of options, what you have in order to fulfill these criteria, what you want to have, right? So now you can choose out of this set of options. I think I will choose here. Yes, the first one, because that has the highest utilization. Here you can check, okay, we take a concrete C3037 with 30 centimeter square rectangle cross section, and with that material and section choice, we go and compute the FEM model, because in the end, I think we want to show that this AI prediction really holds true what we have requested, and we need to prove to maybe a checking engineer or so that these results are correct, and we want to have maybe the FM protocol. So what we do here is set up this analysis again, as we did with the introductory video, define the section, the loads, and compute that, and do the concrete analysis here. Yeah, and in a second, you will see that script running. So very similar to what I've shown you in the beginning. And in addition, here we have this inverse generative deep learning or neural network model to come up with design suggestions for your requested performances. Here it is utilizations in the SLS and ULS. Yeah. And yeah, I will show you if that computation is done. The actual result here. So we wanted it to be utilized in the range of 50 to 100%. And yeah, let's hope that this is the outcome. Go to the concrete. Yeah, you will see here. So it's 76% utilized. So it's a suitable cross section which we can use for the analysis. Yeah, so that's the future of our optimization tool. And if you have questions, feel free to hit the chatbot. Yeah, another thing which Dogukan already showed, I think in some of our prior speaking engagements, is the chatbot, the help chatbot. So that will be a generative AI model which is producing some text which you can chat with. So it's an intelligent manual, so to say, or an intelligent service, what we have here. And how that works, I will demonstrate here. It's based also on the GPT technology in the back end. And for example, I can ask this thing, more for marketing now, what FM6 is. And it will provide you some arguments for using RFEM6. I think that's nice because, as I said, that's a generative algorithm, so it really will chat with you using language. It's having capabilities to talk in German, in English, Portuguese, Spanish, and all the major languages. We have trained that chatbot in our FAQ, knowledge base, and manual data. And as I said, that will be used on the websites and within the programs. So let's now see if that chatbot could also help us with a more specific technical question. Now this time I want the program to answer me or help me if I want to do torsional buckling analysis the ones you're familiar with the Dlubal products, you would know you can do that, for example, yes, with the EC3 module. And yeah, you will find the answer here. So I think that's correct. And the nice feature of that chatbot is, or we intended to have a nice feature here, which is that it will provide you also a reference, an internet source, which you can just click, as you can see here. So that will be an interactive capability here, so that you get the support in due time, that you can really work with that. Yeah, being in generative natural language processing, we have another project which is entity recognition for a text-to-model interface. That is, or the idea is the following. So within the chatbot, or maybe in another window, you are allowed to input natural text. That can be, for example, a command that our text-to-model interface should generate a 6-meter long steel column with a certain material and a certain section from the origin, for example. And entity recognition then collects the main features and maps it to our RFEM code, or this web services code. And how that can work. So this time we played a bit around with a local service, not integrated in the RFEM, but as an extra standing service. Yeah, time will show what the final layout of that will be, but yeah, just that you get an impression for that. So the idea is that you can prompt, so to say, the creation of that model, and then via the web services in the backend, you will see that the API interacts with RFEM, and then this model is created here. You can change that also on the fly if you have decided to model a different thing. So you can just submit your next prompt, and then we'll, via web services, just update the model. So yeah, coming to the end of my presentation of the webinar, I just want to highlight some of the strategy what we are currently working on, and we try to release in the next 12 months, so to say. So we are planning to release this chatbot maybe by end of this year, beginning of next year, and then step after step we will release these text interfaces and also the optimization tools. And in the future, it's also planned to have other modalities, not just text, but also maybe audio, so that you can write and really talk with your Dlubal structural models. Yeah, with that, I really thank you for joining in today. I'm sorry for being gone for a minute or so. Did not realize that, really. And yeah, I would hand over back to Andreas now for the rest of the webinar. Thank you.
Okay, Michael, thank you for your presentation. Yeah, we had some disturbing noises in your voice. Maybe the microphone or the connection to the GoToWebinar server was a little bit bad, but yeah, we could understand you. Okay, before I would like to show you where you can find the recording and the slides, I would like to show you one slide in our presentation. If you have questions to our products, such as web services and API, or you would like to get your free product demonstration of RFEM, RSTARP, any add-on, such as web services and so on, just contact our sales team. You can click on that link or can scan that QR code. You can also get the non-binding offer as you want. Yeah, just contact our colleagues. So then I show you the website, dlubal.com, and under news and events, you can find our webinars. So where's the webinar of today? Those are the scheduled webinars for the next weeks. I click on today's webinar. You will also get an email when the recording is online with a direct link to that page, and then you will find the recording in the middle here. And you can already download the PowerPoint slides as a PDF file. Okay, that's also all from my side. Thank you for your attention. Thanks to Michael for the nice presentation. Thanks to Dogelkan for the help with answering the questions. Yeah, I wish you all a nice rest of the day. A Merry Christmas. If you don't meet each other in a webinar until Christmas. Yeah, and bye-bye.
Bye.
Bye, everyone.